All right, as people are joining in, I will say let's get going. Hello, everyone, and welcome to this seminar as part of our Autonomous Science lecture series at PNNL. My name is Draguna Vrabi. I am a chief scientist and the division director of the Advanced Computing Mathematics and Data Division and the Physical and Computational Sciences Directorate. And I am joined by my colleagues, Venki Prabhakaran, Jenna Pope, and Maxim Zyatidinov in organizing this seminar series that explores the latest advancements in AI, robotics, and experimental science and computational science in combination to develop scientific discovery breakthroughs. And in this seminar series, we are inviting experts who are furthering the evolution of the field. We discuss AI-driven instruments and laboratories and how these systems are transforming the way in which we do science and the way in which we can continue to provide scientific advancements. Today, I am delighted to introduce our speaker, Timur Bazirov, who is the CEO and founder of Exabyte, the company that has its product called Matera, which is a cloud-based platform that enables material scientists to utilize a wide variety of simulation and computational systems and capabilities to explore the development of very complex material science. Matera has dozens of customers in Global 2000 companies, and it currently allows more than 30,000 scientists worldwide to collaborate and build intelligence around the materials design and research and development. With that, I will pass it over to you, Timur.
Thank you very much, Draguna. I'm going to share my screen and get into the presentation. All right. Am I audible? Is the presentation up?
Yes.
Okay, great. First of all, thank you for the invitation. I've been following the previous videos, the previous presentations in the series. It's exciting to be here. Today, I'm going to tell you about how we connect theory and experiment with Matera.com. And I want to start with this quote: theory without experiment is dead. Experiment without theory is blind. So really, when we do science, we don't want to be either blind or dead. We want to be alive and well and see everything that happens. And that's why we need to have both theory and experiment working in a closed loop and driving science forward. Now, if you remember nothing from my presentation, please remember this picture. This is Tolkien's Olli and him using electron microscopy in an automated way where we can have digital twins of the systems that we are working with in real time, and we can manufacture and change the way that matter behaves atom by atom. So that's the picture I want everybody who attends to remember. Now, this is the agenda for the talk. I'll tell you about the company and our product, some of the generic use cases for electronic materials, how we look at the interfaces, heterostructures, layered compounds. I'll cover a specific use case where we enabled closed loop systems for electron microscopy. I'll talk more about synergies with work in other DOE institutions and Brookhaven National Lab in particular, and a little bit about the future outlook. I was born and raised in Russia, came to the United States in 2008 to work on my PhD at UC Berkeley. While I was there, I was always surrounded by smart people working on important problems in material science. But I noticed that the code base, the software that we had to use was dating back to Fortran 77. and it wasn't anything that you would find convenient or easy to use by any means. I set out to change that and started what used to be called exabyte.io, where we first demonstrated use cases for cloud-based high-performance computing in material science. We demonstrated some of the high-throughput simulation workflows. And in 2022, we rebranded as Matera.com, and that's how we operate today. The company name is Matera, which stands for the Era of Digital Materials R&D, and hence the digit in the name. What we really stand for is this evolution, where we have the fourth paradigm, AI-driven R&D, where we have a lot of data, and we need to have different kinds of digital tools that help us take advantage of all this data, and the tools that facilitate fair practices, community-driven science, and AI-driven research in general. In our field, there usually are multiple types of sciences that have to come together, and the main experts, chemistry and materials at the top, people who understand data science and machine learning here at the bottom left, and then people who understand computer science, high performance computing, scaling the infrastructure, and so on. And usually those three are different kinds of people. They speak different languages, they understand different concepts, and our goal at Matera is to build the bridges so that material scientists who work with materials in the lab can utilize the latest data science, the latest artificial intelligence, the latest infrastructure to be able to do their research. And we have this concept of materials R&D cloud, where we have different types of scientists working together and exchanging information. At the center of this is the cloud, which could be public cloud, private cloud. What matters is that it's a focal point where computational scientists, the data scientists, the experimental scientists, all exchange information with each other so that they can collaborate, they can see each other's results, they can deploy any kind of simulations, a multi-scale simulation tool, because we have to be able to deliver insights at different times and length scales. And of course, it has to be a secure system, and there has to be some visibility for the R&D management. Today, we have over 100,000 calculations run, 50,000 material structures, 30,000 scientists, PhD level scientists that collaborate and use our platform worldwide. And mostly our main value proposition is that we take research that comes from academic institutions. And a lot of computational material science is still driven by academic institutions today. And we help apply it in a more time-constrained environment that large enterprises and the R&D institutions operate in. So somebody in academia can have different types of problems that they're interested in. By the time we take their solutions, and we mostly work with open source code base, and put it into our platform, they can be applied in a high throughput manner. The data is well organized, it's ready for AI, and that's where we focus. All right. Now, let me show you how the platform works in practice. We have different steps through the R&D materials lifecycle. We start with designing structures, we design modeling workflows, we provision the infrastructure for high-performance computing, we control the execution of simulations, collect data, organize it, and then build analytics and AI, and do experimental validation. So today, if somebody comes to our platform, they would start with designing a structure. So in this case, it's a aluminum gallium arsenide interface, or it's a hydrogen storage material where we can look at chemical reactions. And then if they are experts in theory, usually there's many other parameters that they have to set. But for someone who is not an expert in theory, but works with these materials in the lab, we provide a set of templates where this newly created material can be characterized in silico using a workflow. In this case, I'm using electronic band structure workflow. There are multiple other templates that we have created. There are multiple other contributions from our community. So we take this workflow and apply it to the material. And then at the third step, we also select computational infrastructure where we want to run. Different types of computational resources are available. We work with Microsoft Azure for a long time and other cloud providers. So this three-step process simplifies the setup for a computation. And then as a next step, users would submit this for calculation, wait until the calculation is done. And at the end, our platform extracts the results and shows it to the user in form of a graph or a data point. Of course, as we go through high throughput characterization, when we have multiple different materials that we want to look at, we need to be able to run this in some sort of automated fashion. And we support that through a RESTful API. So if somebody wants to screen thousands of different combinations of these compounds, they can do that in Pythonic ways. And there is a setup for someone who prefers to use command line to work with a platform through command line as well. So these are the basic usage aspects of the platform today. Now, let me talk through some of the use cases, and I would like to highlight specifically semiconductor materials, electronic materials, and thin film use cases for this presentation. There are multiple other use cases that we've been working with our customers on, but thin films and electronic materials is still the most developed area. So we start with designing materials, and for many of the realistic structures, including defects and disorder, this is not an easy process. So we have to start with, this is how a platform looks to a user. This is an account, for an example, organization. And these are all materials that are being tracked inside the account. We have them uploaded into a database, and people can search through these materials using a set of pre-selected search entries, or they can create arbitrary custom search entries themselves, search queries. These are some of the possibilities that we support in a materials designer. So many realistic real-world effects depend on the disorder and defect dynamics. And lately, we've been investing into the functionality that we call Matera 2D to be able to work with defects, with the surface defects, with point defects, with defects dynamics. And these are some of the possibilities in terms of the design. The process here is where we have configuration, so a set of items that exist before we built a complex material. And then we have a transformation where we use a builder, and then we have a set of outcomes. In the case of creating an interface, we start with a slab configuration for film, we start slab configuration for a substrate, and then we apply a certain algorithm to match film with the substrate, and as a result, we get a set of candidates depending on the strain, and we can pre-select and identify which strain we would like to get. Lately, we've been active with the Department of Commerce, with the National Institute of Standards and Technology, and this is part of our work with them still ongoing, where we set up a categorization framework for creating materials based on the process, where we start with pristine structures or compound pristine structures when we combine two slabs together, with defective structures where we introduced things like disorder and making things amorphous. And then we also need to understand some sort of processing in chemistry and passivation and so on. So this is a recent paper that we put out with M codes. So a quick tag that can tell us the type of structures that we work with and its evolution and dimensionality. For each of these use cases, we have Jupyter notebooks that are available as part of the platform and the open source, and they demonstrate how to create each of these material types. And they represent a set of workflows that someone can execute to be able to create an interface, create a nanowire, and many other different arrangements. This is all open source and available online. Now, after we created the material, we need to understand how to characterize it. And I'm going to highlight a specific workflow that calculates valence band offsets. So we start again with a list of different workflows. This is how it looks like to our platform users. And you see that it's a big list of different possibilities. I'm going to highlight the valence band offset calculation here, and that's how someone would get started. They would import a heterostructure. In this case, it's a moly sulfide and I think moly telluride heterostructure where we place the two materials on top of each other. And then to be able to calculate the valence band offset, we have to do multiple things. And this is a sub workflow that deals with the interface, where we calculate self-consistent field unit from density functional theory, and then we calculate average electrostatic potential across the cell, and then we repeat that for the top part of the interface and then the bottom part of the interface. So if we represent this workflow in terms of individual units, you can see that it becomes quite complex very quickly. So for someone who is just getting started with Quantum Espresso, that's the engine that we use underneath it, or potentially some other DFT engine, it becomes prohibitively difficult to deal with this complexity without having specialized experience. But in our platform, we summarize it to a user as part of the workflow. This is how the workflow looks like to a user. There are larger building blocks, and then there are smaller building blocks as units. And each of these are meant to be like Lego blocks where users can swap and modify some of the parameters of these workflows. So this is how a calculation would go for someone who wants to calculate the valence band offset. They would come into our job designer, get started with selecting a material. And in this case, I have the interface between to the two materials that are present here. And then the third material here is the interface. And then they select valence band offset as a workflow. And if they want to modify parameters that are specific to the engine that we use, they can do that with the help of our interface. When they know exactly what they want to change, they're able to get to that point and zoom in into the workflow and change it. We also highlight important parameters like key point sampling, some of the wave function cutoffs as part of the interface for people to be able to change in many places at once. Last step is to select the infrastructure. Again, these are different types of cloud providers that we support today. There's 3 major cloud providers, and then there's a fourth one, which is free for academic usage. So anybody who wants to run calculations with us can do that for free on Cluster 101. And in each of the clusters, they also have different types of hardware available, the GPU-enabled hardware, CPU-enabled calculations, and then some spot-based computing as well as saving resources. So once the calculation is done, we wait for it to complete, and at the end, we get the average potential profile across the interface and the value of the valence band offset. So we took quite a complex workflow, and we made it consumable by scientists that don't necessarily have expertise in the computational domain, but they can understand the interfaces that they work with. They understand the types of problems that are important for this kind of interfaces, and that's the fundamental enabling aspect. Now, as we go through this process multiple times, we have a set of properties that accumulate that are calculated for specific materials as part of specific jobs. And that's the property view in an example account. We can search through the properties. We can understand which materials they belong to, what are the precision metrics that were deployed during the calculations. Was it just somebody fiddling with a new workflow, or was it a production type calculation? So there is a way to get through all of this information with the help of our platform. And lately we have demonstrated how to use how to make data interchangeable with third parties. So in this case, I'm highlighting the effort from NIST. They have this Jarvis infrastructure built by Kamal Choudhary, where it's similar to a materials project where we have data that represents specific types of materials. And we demonstrated a way to ingest and get data from gyros and then potentially use that for calculations as well. Here we have an example of how we can take data and use a RESTful API to insert it into a database. We take a postcard file that represents a particular material in materials project, and then we use Matera's API to import data from this material. And there's a set of notebooks where we demonstrate how we can run simulations on multiple materials at once, extract properties from them, and store them in a database. Now, as a next step, I'd like to focus on the use case that we developed together with the University of Tennessee group, led by Professor Kalinin, and focused on STEM, electron microscopy use cases. As you can see, the first step for connecting experiment and theory is to connect the people to understand the problem. This is me visiting their setup. This is Sergey visiting our office in California. And this is the systems that they work with. So high resolution microscopy, so then they can get down to the atomic level, resolve positions of individual atoms. And what they get from experiment is this setup where there's the 2D material, and then as beam shines on this 2D material, it gradually deteriorates. So there is a time resolution data on how defects and cavities are formed inside this material. And this is an animation of what they see from experiment. Now, using a bit of Python and some image recognition, they're able to extract coordinates from the images that they work with. And then as a next step, they've used Matera API to be able to upload the resulting structures into a platform. So there's a drop-in capability where once you have an API token in any Python pipeline, you're able to communicate with Matera servers and then send out the structural information to us. So this is how the movie looks like inside Matera's platform. So each of these are individual snapshots. And you can see there's it's graphene with some of the silicon atoms scattered across. And this is about 1,600 atoms, so 40 by 40, roughly 40 by 40 2D cup. What can we do after we have this information in Matera? We can look at it to begin with. We can understand and do some measurements and try to do some initial analytics just based on the way that the systems look. And then here I'm going to demonstrate what is supported. So if we look at the particular structure and the cavities formed inside it, we can understand the distances at which the cavities are formed, and that's what we support natively as part of Matera. And then if you do that through a significant period of time, there is a way to come back and search for particular structures using formula, using some metadata that we extract during the upload. And there are ways to write more sophisticated queries and maybe save them for reuse. So if you want to find a particular structure, you don't have to retype the query every single time. But most interesting aspect is when we start including simulations. So this is a set of workflows that are available inside Workflows Bank. So template workflows that are curated by the team of curators of the Matera platform, which mostly includes our internal team plus some people that we work with as collaborators. And here is the fixed cell relaxation workflow that we can copy from the bank, and we can apply this workflow to data that we get from STEM. And it's relatively simple, just a single step relaxation workflow in this case. And what we did there is we used the Python API again to be able to utilize a relaxation and include it into the mix. So what we started with is this flat two-dimensional material, because in the experiment, there is no way to resolve the z dimension, right? We would just put all the atoms at the same level. We understand where they are on the xy plane, but z is not quite there. So we start with this structure, and what we do is we run a relaxation that can tell us where on the z plane the atoms actually are. And with the help of a little bit of Python, we get to the point where we can understand the heat map of how far out of the plane each of the atoms are. And that can tell us that there's likely defects or some sort of maybe interesting effects that are happening right next to those red points. And the idea here is that we can have a closed loop system where we send data to the cloud, do processing, so 3D reconstruction in this example, and then we send feedback to the instrument and try to make this instrument do something. And in this case, it could be either a focus on a particular atom or move beam to a different part of the sample. So understanding how to utilize this extra data that we get from 3D reconstruction to be able to manipulate the original instrument. Now, let me talk a little bit more about the approach and how we implement all these different bits and pieces of the Matera platform. Unlike many others, we are very adamant and very vocal about data standards. And we put a lot of effort internally and then open sourced a lot of the information that we work with. And we believe that it's data standards that really facilitate the ability to automate much of the work that we do. And on the left, you can see here are open source components of the Matera ecosystem, and that includes the data standards themselves, the extractors that allow us to take data in the native formats, like in case of Quantum Espresso or WASP, those would be native formats for those applications, and then extract the data into compliant format. And then we have a set of applications like the Materials Designer application that I highlighted to you before, that is in the open source domain as well, and works with this particular standard. So our goal is to be able to support this open source development and then integrate this into a Matera platform for enterprise applications, for people who need extra compliance, security, and all of this. Important, but not creative details usually. And then we support external elements. So if someone has a cluster, they want to deploy a platform ad, or there is a laboratory equipment, as we just demonstrated with the STEM use case, or there is a specific data platform, we can interact with it with the help of a RESTful API. Much of our code base is open source. If you go to our GitHub page, these are some of the repositories that we highlight. Again, the data standards, extractors, API examples, how to work with the platform, and different types of open source applications, visualization packages, and so on. When we talk about data standards, we start with ontology. So what kind of entities we deal with and how they are connected to each other. And this is a brief explanation of the ontology that we use. We start with a material structure. We have a workflow that includes a particular model in our case, and the model itself can be subdivided into smaller bits and pieces depending on how complicated the workflow is. And then by combining material and workflow, we get a job, and the job gives us a particular property which is characterizing the original material. And then there usually is a precision metric attached to this property. Now, when we deploy these different models, we have a set of different techniques that we need to categorize again. So we came up with this relatively simple and in no way complete, but practical categorization where we have physics-based models at different level categorized, and including a set of tags that we can add to them. For example, if somebody deployed density functional theory and then added spin orbit coupling, there is a way to for our system to know that once the calculation is created in Matera. And then the third portion when we talk about data standards are schemas. So how do we actually structure the data, what is being stored in a database, and how we can run queries on it. So on the left is an example schema for a material that we track inside open source repository called ESSI, which stands for Excellent Source for of Schemas and Examples. And then we can see that it has a particular structure, and there's a crystal lattice, crystal basis, material formula. And on the right is data structure that adheres to this particular schema. As I mentioned before, we had have an ongoing collaboration with NIST, and there is a way to track third-party schemas inside this repository with the goal of being able to move data back and forth smoothly. Now, the next step is in designing workflows that are built on top of these data standards. And here I'm looking at a workflow designer package and a set of building blocks that we call flavors that represent different parts of these complex workflows. In particular, this is a usual first step in any kind of density functional theory calculation from plane wave pseudo-potential approach. And you can see that there are multiple different flavors that we track inside our system, and those can be pre-selected by users. And on the left, we can see a workflow that utilizes such flavor. So instead of going down to minute details of how quantum espresso input files look like, we want our users to be able to focus at a high level and combine these different Lego blocks together in the arbitrary fashion that can represent the complexity of materials and applications that they deal with. And of course, this is all dynamic. There are multiple different packages being developed, and there are people who continuously write and introduce additional capability into it. So our goal is to be able to connect the developers of these tools with a scientific community, people who may not be comfortable understanding the Fortran, C, or even Python for that matter, but they can utilize our platform and its user interface to be able to deploy new updates coming from model developers and adopt them for their specific materials use cases. Now, I was talking about the theory and simulation capabilities in organizing data for it, but the concept itself is applicable to experimental equipment as well. When we talk about workflows, when we talk about flavors, when we talk about different types of standards, we can swap simulations and talk about experimental equipment and the data standards that it produces, the workflows that are used to operate this experimental equipment. And we found this interesting analogy with the work out of the Brookhaven National Lab and their system called Blue Sky. And if you look at the ontologies, their system has multiple different interfaces, including device, detectors, and all sorts of variations of different experimental related systems. But at the core, it still represents an ontology, and it's a similar approach in spirit. And then they also have a set of schemas that can be utilized to organize this information and for tracking metadata, for tracking provenance, for tracking what happened with experimental results. And there are ways to build custom workflows, custom applications with the help of their Pythonic interface to reflect on a specific setup that experimentalists are dealing with. So in principle, it should be possible to apply the same approach with designing reusable workflows, with connecting what we have built at Matera and what is possible with the work of Brookhaven National Lab to build closed loop systems. And that's what we've been exploring lately. It's in early stages, but active discussions. So let me now transition and summarize briefly what I've just explained to you. Today, we can ingest experimental data and store it on the cloud, of course, to make it searchable and enable collaboration. So if you have an instrument that feeds data into the cloud and you're traveling somewhere, you can see what kind of data you're producing. And if you automate the process, it becomes controllable as well. We've shown how to incorporate modeling and simulation capabilities to assist with some of the analysis, and in principle, how to make decisions on the next course of action based on theory in the loop. And the step that we're currently working on is to close the loop and automate the process of moving the instrument and running this inside a repeated flywheel. Now, today we only looked at one particular simulation workflow, but what we should have is a progression where we have multi-scale, multi-tiered theory. Ideally, we can run this theory as quickly as experiment, so that there is no need to run DFT calculation and wait for hours. We can have a foundation model that understands the system that we work with and gives us essentially a digital twin of the instrument so that the instrument can be controlled and optimized. Now, I'd leave you with this picture and the video from Sergey's Nature paper published back in 2016, where the concept of the atom forge was introduced. So with the capability that comes in a closed loop system where we have theory and things like the data construction, spectra and simulated a closed loop data exchange, with a digital twin, what our goal is to enable this manufacturing loop at the atomic scale, where we can manipulate systems and try to get it to the point where we can build out specific atomic arrangements in the real world with the help of both theory and experiment. And that's what has been introduced back in 2016 as part of the atomic forge. Okay. I'll leave the summary here for everybody. And with that, I'd like to thank everybody for your attention and answer any questions.
Awesome. Thank you. Sorry, my Zoom is like freezing. So I will be the moderator for the question and answer session. But I actually wanted to ask a question first. So you guys have this really like comprehensive fleshed out workflow that incorporates, you know, a number of advanced techniques. What, in your opinion, is the thing that's like hindering the widespread application of advanced AI models into industrial R&D rather than just, you know, more academic or lab-based R&D?
That's a great question. I think in many cases, the problem is with the complexity of the materials that industrial players are working with, and optimizing for repeatability as opposed to a frontier science. So there are certain effects that might actually be relatively straightforward, but if you look at it in a context of an academic lab, you might not get published or just not considered to be state of the art. But those things might be very important for manufacturability, for the engineering applications. So I think there is some disconnect in terms of just understanding which problems are important on each side of the table. And then the second portion of it is ability to extract data from experiment at high enough velocity. A lot of the problems that we are able to solve with AI, and AlphaFold is a good demonstration, right? Where we have experimental data coming from a PDB database, we're able to train AI, and it's extremely impactful. It does things that we didn't expect it to do. But that's because we had this repository of high quality experimental data. And a lot of the problems that we're dealing with in materials just lack this capability and lack this source of reliable, high resolution experimental data today.
Yeah, or it could be the industrial experimental data is kind of like behind their firewall, right? And not shared widely.
Right. Yeah.
Let's see. Vinky, I just saw that you posted a question. Do you want to unmute and ask it?
Sure. Yeah. Thank you, Timur, for the excellent talk. It was quite fascinating to see what Mantra can do for us. I was wondering whether you could extend to support something like an XF's workflows, where when we collect those, I'm an experimentalist, so when we collect those beamlines, in the XF spectrum in the beamlines, we wanted to generate or do some structure analysis quickly over there, and then compare with our XF's data so that we can modify do something about it, right? Most of the time it's done offline, where the beamline times are precious. So I was just wondering whether this could be possible to predict something like an on the fly.
Yeah, I think we can talk about it in more details, but there might be even opportunity to do it across multiple labs, because as part of the discussion with BNL, I think this is what they're interested in as well. And
sure, I bet.
With this, with Mission Genesis and all the other interesting efforts that come out, having a collaboration across multiple labs might be interesting.
Sure. Yeah, we'll be in touch.
Yeah, hopefully that Genesis call will come out soon, so we can start with some of that stuff. Let's see. Jindal, you also have a question. So if you would like, please go ahead and unmute yourself.
Hey, can you hear me okay?
Yep.
Yes.
Wonderful. Thank you very much for the talk. I see that you also have data analytics, ML model development, and things like that. So when you do ML model development, is it possible to gain physical understanding, or it is more like data-driven model?
So when we say modeling, we talk about physics-based modeling.
Okay.
And that's how our platform was built historically. But over time, as we get a data set of physics-based results, we can start building foundation models. So that's where the machine learning, the artificial intelligence comes in. But artificial intelligence is great at seeing patterns and filling in the gaps. But in terms of understanding physics, I think there are certain limitations. That's why we rely on physics-based data, and that's why experimental data coming into the mix is critical.
Thank you.
Yeah.
All right. Does anybody else have any questions? If you want to raise your hand or put it in the chat.
I have a question, or a couple of questions. So first, thank you for the really good talk. So I was wondering, I was wondering, how are you combining the computational aspects with machine learning, especially knowing that every time you run a simulation, you pay a computational cost? Are you thinking about ways in which you can utilize active learning or multi-fidelity modeling to lower the computational cost for some of the experimental, like larger scale experimental runs that a user may want to do?
Yes. So in the example that I've shown, we have 1,600 atoms, which is a sizable structure for doing calculations from density functional theory. It's not impossible today, but we're going to have to wait, and the infrastructure that's required to do that is quite large. But instead, we could use a foundation model that is trained on DFT data for a particular system and run a calculation using machine learned potentials. So we use different type of theory that is trained on data that comes from theory that's more advanced. That would be one approach to try to have a digital twin of real world complex experimental systems where we built out a multi-tier, multi-scale sort of in the loop capability that doesn't require you to wait for too long. Does that make sense?
Yeah. So I'm also wondering, how do you quantify uncertainty in that context, and how do you use that information to?
Uncertainty meaning how far the theory is from experiment?
Yes.
That's a great question. I think we're going to have to do the measurements in the end. But there are certain ways that we can try to perfect the theory, but in the end, without experiment, it doesn't work. So what is good is that we can do more theory than experiment, and then experiment can give us the trend, right? So the data that comes from experiment in most cases is expensive and sparse, but as long as we can have data points and the theory gives us the trends, we can try to come up with intelligent ways to reduce experimental burden.
Thank you.
That's where the throughput, I think, is also critical. One of the items that electron microscopy provides in particular, and to beamlines too, is having data at high throughput. And I think with enough throughput, we're able to utilize foundation models and AI much more efficiently.
Thank you.
You're welcome.
Michael, go ahead and unmute yourself for your question.
Hello. So I know you mentioned, I believe it was Quantum Espresso and other programs. There are, of course, many, many, many ab initio programs out there. I know around the lab, NWChem, CP2K, LAMPS, GROMAC.
Yes. Yeah.
For those not already supported by Matria, what would be involved in adding an additional DFT code?
That's a great question. We're currently working on a tutorial which will explain exactly how to do that. Lately, we've been setting out examples of how somebody can compile a container, and we use Singularity Obtainer in our latest platform to make it portable and to make it extensible. So if somebody comes in with a new version of Quantum Espresso with a new package that we don't support today, it would start from the infrastructure layer where we work with you or you independently compile a container. And then there is this repository where we track, go back here, where we track the Lego blocks, right? So there is a repository where we track workflows, different individual building blocks for the workflows. We're going to have a pull request into that repository to define at least some of the examples. And then when we agree on the approach and we merge it into a master code base, and that can be deployed to Matera. So ideally, there will be a two-step process where we compile the executable in a portable way, and then we create example workflows and building blocks accordingly.
Thank you.
We would love to discuss more if there is a specific requirement.
I don't have one offhand. I was just checking whether or not there was a built-in restriction to certain programs or not. And it doesn't sound like there is.
Well, as long as you don't use it to mine Bitcoin, I think we should be okay. As long as it's scientific and that's something useful for the community.
Sure. Thank you.
Anybody else have any more questions? Okay, if not, let's think some more again. And thanks for the great talk and looks like there's a lot of cool stuff going on at Mantria, so I'll have to try that out.
Please.
Awesome. And thanks everyone for joining as well. Have a good
Thank
day.
you.
Good day.
Thank you.